Hey folks, most of us know by now that one way to make code faster is to run it in parallel, that is, if you can. And most of us know by now that Python code can sometimes be made faster by converting it to C with Cython. In this video, I'm going to combine both of these techniques. I'm going to show you the basics of writing Cython code that uses native parallelism. Now, by native parallelism, I mean Cython code that runs in multiple threads, but without using the overhead of Python's threading system. Instead, your C module uses the OpenMP standard for parallel processing, so it'll run in parallel on any platform that supports OpenMP. Linux, macOS, and Microsoft Windows all support OpenMP. Now, there's a few different ways you can employ parallelism in Cython, and in this video, I'm going to start with one of the most basic and immediately useful, the parallel range construction. So let's take a look at an example. This Cython module has two versions of a function. Both do the same thing. They take in a value, n, and they create an incremental sum by looping n times. The first version of this just uses the range object, which in Cython is lowered to C types for maximum speed. The second version uses the Cython.parallel module's prange, or parallel range function. The idea here is that we run multiple copies of the range loop in separate threads, each copy covering a different portion of the range, so they all complete in parallel. Any values we create or manipulate in the loop are handled according to certain rules. For instance, with sum, we're using an in-place operator, plus equals. If we use in-place operations in a prange loop, the resulting values from each thread will all be reduced or merged using the same operation. So all these additions from separate threads get automatically consolidated into the same variable at the end. On the other hand, any variables we created new inside the loop for thread local processing aren't going to be available after the loop block. So you're going to want to carefully read the directions for how prange works to make sure your assignments inside the loop give you the results you want. We also have a hint here that the loop should be performed outside of the GIL. That's optional, but it means the rest of our Python program doesn't have to wait around for that loop to finish. It also means any work we do inside the loop must be on pure C types. We can't use any Python objects there. Finally, we have the schedule option. This lets us tell the OpenMP backend how to handle scheduling of work in each thread. Static is the best choice for when the workloads are all heavily predictable, since all it does is parcel the workload evenly across each thread. But if the workloads have a lot of variance in their runtimes, you will want to try playing with the other options to see which yield the most efficient results. The docs go into more detail about the ways the other options work, and we may explore those in other videos. It's also possible to specify how many threads to use, but the default is just to let the runtime decide how many threads to launch based on the number of available cores. Now, to run this code, I'm using two different workloads. One sums to 100 million and shows the results for both the serial and parallel versions of the function. The other sums to only 5,000, also both serial and parallel. Now you'll notice when I run this code, the 100 million iteration version shows a substantive reduction in runtime, about 4 times faster. We could probably speed it up further from that with some more tweaking, but that's enough to give us an idea. But with the 5000 iteration version, it's the other way around. The parallel version is almost 10 times slower. What's going on here? And this is something that persists across multiple runs. This isn't something that only happens on the first run. Well, the answer is simple. This is a classic case of the overhead of threading far outstripping the overhead of the actual processing you're doing. There isn't always an easy way to tell if a given workload is going to be faster with threading versus without, but the golden rule is the larger the workload and the easier it is to parallelize, the larger the improvement you'll see over serial processing. Now, I've only introduced here a simple example, but this should be enough to help parallelize some basic workloads. In future videos, I'm going to go into more detail about how to do parallel work in Cython with more complex structures like NumPy arrays, and I'll also be demonstrating some of Cython's more advanced parallelism features. So that's it for this episode. If you liked it, leave a comment below, and don't forget to follow Dev with Serdar and InfoWorld on Facebook, YouTube, and InfoWorld.com.